Particles from exploded stars are passing through your body right now, traveling across the galaxy at nearly the speed of light, and most people never realize it is happening. Some of this invisible radiation helped shape Earth's atmosphere, influenced planetary survival, and may have even contributed to the chemistry that made life possible. Tonight, we are following the hidden connection between cosmic rays, magnetic fields, and the evolution of habitable worlds across deep space. Welcome to Relaxing Facts Studio, where real science, space mysteries, and planetary discoveries come together through calm, immersive documentaries designed to make the universe feel both understandable and astonishing at the same time. Tiny particles are passing through your body right now, and most of them began inside exploding stars millions of years ago. A single square centimeter of Earth receives thousands of these impacts every minute. The process starts when a massive star collapses in a supernova explosion, accelerating atomic fragments through shock waves powerful enough to push matter close to the speed of light. Most of these particles never slow down. They cross the galaxy for millions of years. That constant stream becomes dangerous only when it collides with something solid, especially an atmosphere. High-energy protons strike oxygen and nitrogen molecules in Earth's upper atmosphere, triggering particle cascades called air showers. One incoming cosmic ray can generate billions of secondary particles before the energy finally dissipates. Some of those particles still reach the ground. Others penetrate deep underground and even through ocean water. The atmosphere absorbs most cosmic radiation before it can damage living tissue, but space offers almost no protection at all. Astronauts aboard the International Space Station receive far higher radiation exposure than people on Earth because magnetic shielding weakens with altitude. Mars faces an even harsher problem. Its thin atmosphere blocks far fewer energetic particles. The difference is enormous. Earth's atmosphere equals roughly a concrete wall nearly 30 feet thick in shielding power. That shielding matters because cosmic rays arrive with extreme energy levels that human technology still struggles to reproduce. Some particles carry more kinetic energy than protons accelerated inside the CERN and its Large Hadron Collider. These particles travel across distances larger than entire spiral arms of the Milky Way before reaching Earth. The galaxy is never quiet. Space is filled with invisible radiation moving continuously between dead stars and developing planets. That continuous radiation means planet evolution is never fully isolated from deep space events. A nearby supernova can increase cosmic ray exposure for thousands of years, altering atmospheric chemistry and radiation levels across entire planets. Scientists have found traces of radioactive iron-60 in ocean sediments, evidence that material from ancient stellar explosions once reached Earth directly. The particles are microscopic. Their planetary effects are not. High above the clouds, invisible particle collisions are constantly changing the chemistry of Earth's atmosphere. Cosmic rays slam into oxygen and nitrogen molecules at altitudes where commercial aircraft rarely fly, releasing bursts of secondary particles and ultraviolet energy. Those impacts break stable molecular bonds apart within fractions of a second. The atmosphere does not stay chemically still. It reacts continuously to incoming radiation from space. Those reactions become important because broken molecules quickly recombine into entirely different compounds. When cosmic radiation splits oxygen molecules apart, free oxygen atoms can bond again into ozone, forming part of the protective ozone layer that absorbs harmful ultraviolet radiation from the sun. Other collisions produce nitrogen oxides, which influence cloud formation and atmospheric circulation patterns. Small chemical shifts can spread globally. Jet streams move these compounds across continents within days. The same radiation that helps create protective atmospheric layers can also destabilize them under different conditions. During intense solar storms or nearby cosmic events, excessive ionization increases chemical reactions that temporarily weaken ozone concentrations in parts of the atmosphere. Earth usually recovers because its magnetic field and dense atmosphere distribute the energy over time. Mars could not maintain that balance. Its thinner atmosphere lost much of its protection billions of years ago after its magnetic field weakened. That imbalance changes entire climates over geological timescales. Cosmic rays influence atmospheric ionization from the upper stratosphere down toward cloud-forming regions, affecting how water droplets cluster and how heat circulates through planetary systems. Scientists studying ice core records have linked long-term radiation fluctuations to measurable changes in carbon isotopes and atmospheric chemistry cycles. The scale is planetary. A single energetic particle can trigger reaction chains extending across thousands of cubic miles of atmosphere. Those chemical reactions suggest that planetary climates are shaped not only by stars and oceans, but also by deep space radiation arriving from distant supernova remnants. A planet may orbit inside a habitable zone and still struggle to preserve stable atmospheric chemistry if radiation levels remain too extreme for long periods. Habitability depends on balance. Too little atmospheric interaction limits protective chemistry, while too much radiation slowly erodes the same systems that protect life. Long before life existed on Earth, energetic radiation was already changing the chemistry of the young planet. Cosmic rays struck simple gases in the early atmosphere, including methane, ammonia, water vapor, and carbon dioxide, forcing stable molecules to break apart and reconnect into more complex structures. These reactions happened constantly across oceans, volcanic regions, and upper atmospheric layers. The early Earth was chemically active. Radiation supplied part of the energy driving those reactions forward. That energy mattered because simple molecules rarely organize themselves into larger organic structures without an external trigger. When cosmic radiation ionizes atoms, electrons separate from their normal positions, creating unstable fragments called free radicals. Those fragments rapidly bond with nearby molecules, producing increasingly complex carbon-based compounds over time. Some experiments have reproduced this process in laboratories. Under radiation exposure, simple gases can generate amino acid precursors and nucleobases connected to biological chemistry. The same radiation capable of building complex molecules can also destroy them if exposure becomes too intense. High-energy particles break molecular bonds indiscriminately, damaging fragile organic structures as easily as they create them. Earth's oceans and atmosphere helped moderate that problem by absorbing much of the incoming radiation before it sterilized the surface completely. Airless worlds face harsher conditions. Without atmospheric protection, organic molecules on exposed surfaces degrade far more quickly under cosmic bombardment. That balance may extend far beyond Earth itself. Scientists have detected complex organic molecules inside meteorites, interstellar dust clouds, and comet material traveling through the solar system. Some carbon-rich meteorites contain amino acids formed before Earth even existed, suggesting radiation-driven chemistry operates across enormous interstellar distances. The process is surprisingly widespread. Molecular complexity can emerge anywhere energy, carbon compounds, and time overlap long enough. Those discoveries change how scientists think about the origins of life. Instead of requiring one extraordinarily rare event, prebiotic chemistry may develop naturally on many young planets exposed to moderate radiation and stable environmental conditions. Cosmic rays may act less like a destructive force and more like a planetary chemistry engine operating silently over millions of years. Life may still be uncommon, but the chemical ingredients behind it appear far less isolated than scientists once believed. Deep beneath Earth's surface, liquid metal is constantly moving around the planet's core, generating a magnetic field that stretches tens of thousands of miles into space. That invisible shield deflects large amounts of incoming cosmic radiation before it can directly strike the atmosphere. Without it, Earth would absorb far more energetic particles from solar storms and deep space cosmic rays every day. The protection is enormous. Most people never notice it happening. That shield forms because Earth's outer core contains electrically conductive liquid iron moving through convection currents driven by internal heat. As the planet rotates, those flows organize into a global magnetic system called the geodynamo. Charged particles approaching Earth become trapped or redirected along magnetic field lines instead of penetrating straight toward the surface. Some particles still enter near the poles. They collide with atmospheric gases and create auroras visible from space. The difference between protected and unprotected planets becomes clear when comparing Earth with Mars. Evidence suggests Mars once possessed a stronger magnetic field billions of years ago, along with thicker surface water systems and a denser atmosphere. After its internal core cooled and magnetic protection weakened, solar wind gradually stripped atmospheric particles into space. The loss happened slowly. Over hundreds of millions of years, Mars transformed into a colder and far drier world. That transformation affects entire planetary systems, not just surface weather conditions. Magnetic shielding helps preserve atmospheric pressure, stabilize liquid water, and reduce long-term radiation exposure across global environments. Jupiter's magnetic field extends so far that it could fit the Sun inside parts of its magnetosphere, while smaller rocky planets often generate weaker protection. Size matters here. Larger planetary cores can sustain internal heat and magnetic activity far longer than smaller worlds. That relationship means habitability depends on more than distance from a star. A planet may sit inside the so-called habitable zone and still lose its atmosphere if magnetic shielding collapses too early. Scientists searching for potentially life-supporting exoplanets now study magnetic activity alongside temperature, water, and atmospheric composition. A stable planet requires layered protection. Without magnetic shielding, cosmic radiation slowly reshapes atmospheric chemistry until long-term habitability becomes increasingly difficult. Even while we sleep, the universe keeps interacting with Earth in ways we rarely notice, shaping atmospheres, influencing planetary survival, and possibly helping complex chemistry emerge long before life begins. Cosmic radiation is not just distant space activity. It is part of the story of every habitable world. Thank you for watching Relaxing Facts Studio. If you enjoyed this episode, please subscribe and turn on notifications so you never miss future documentaries. Like the video, share it across your social media pages, and leave a comment with your thoughts or the most surprising fact you learned today. Your support truly helps this channel grow, continue, and reach more curious minds everywhere.